What's up mga iis?
Robots are an indispensable part of today's large manufacturing industries. These intelligent machines have taken over many of the tasks requiring high precision, speed, and endurance. They are becoming smarter, more flexible, and more autonomous with the capability to make decisions and work independently of humans. Early industrial robotics in manufacturing from 1954 to 1979. Early industrial robots had limited intelligence, autonomy, and operational degrees of freedom. They were mostly designed to perform one or two sets of repetitive tasks in a highly controlled environment. The earliest example of industrial robotics came about in 1937 after inventor Griffith P. Taylor built a crane-like device powered by a single electric motor. It had 5 axes of movement. Most important were the grab and rotation functions, which could stack blocks in a pre-programmed movements. The first industrial robot was designed by George Devol in 1954. This robot was capable of transferring objects from one point to another within a distance of about a dozen feet. Famulus was developed by German robotic company KUKA in 1973. It had 6 electromechanically driven axes. The silver arm was developed by Professor Vector Schinman in 1974. It was capable of performing small part assembly jobs using feedback from touch and pressure sensors. ASEA IRB was built by a European company called ASEA in 1975. It was the world's first fully electrically driven robot. It was also the first microprocessor-controlled robot and used Intel's first chipset. Modern industrial robots from 1980 up to present day. From 1980, industrial robots began to made in large numbers, with a new robot being introduced in the market at the rate of 1 month. These robots are microprocessor-controlled and are smarter and have higher degree of operational freedom. The first robotic arm with motors installed directly into the joints of its arm was built by Takeo Kanade in 1981. This design made it faster and more accurate than previous robotic arms. Industrial robots are increasingly becoming more intelligent and versatile. In the future, they are expected to be capable of working without human intervention and take over most of the manufacturing processes. Robot generations. Engineers and scientists have analyzed the evolution of robots, marking progress according to robot generation. First generation. A first-generation robot is a simple mechanical arm. These machines have the ability to make precise motions at high speed. Such robots find widespread industrial use today. The operation of these machines must be constantly supervised because if they get out the alignment and are allowed to keep working, the result can be a series of bad production units. Second generation. A second-generation robot has rudimentary machine intelligence. Such a robot is equipped with sensors that tell it things about the outside world. These devices include pressure sensors, proximity sensors, tactile sensors, radar, sonar, lidar, and vision system. Second-generation robots can stay synchronized with each other without having to be overseen constantly by a human operator. Third generation. The concept of third-generation robot encompasses 2 major avenues of evolving smart robot technology: the autonomous robot and the insect robot. An autonomous robot can work on its own. It contains a controller and it can do things largely without supervision, either by an outside computer or by a human being. Fourth generation and beyond. Any robot of a sort yet to be seriously put into operation is a fourth generation robot. Example of this might be the robots that reproduce and evolve, or they incorporate biological as well as mechanical components. Industrial robot components. Controller. The controller is the brain of the industrial robotic arm and allows the part of the robot to operate together. It works as a computer and allows the robot to also be connected to another system. Robot arms. Industrial robot arms can vary in size and shape. The industrial robot arm is the part that positions the end effector. End effector. The end effector connects to the robot's arm and functions as a hand. This part comes in direct contact with the material the robot is manipulating. Some variations of an effector are the gripper, vacuum pump, magnets, and welding torches. Drive. The drive is the engine or motor that moves the links into their designated position. The links are the section between the joints. Industrial robot arms generally use one of these following type of drives: hydraulic, electric, and pneumatic. Sensors. Sensors allow the industrial robotic arm to receive feedback about the environment. They can give the robot a limited sense of sight and sound. The sensor collects the information and sends it electronically to the robot controlled. Configurations. Cartesian. The base x-axis of the Cartesian robot is generally supported along its entire length, but the y or z-axis is cantilevered. A Cartesian system is one that moves in three orthogonal axes, the x, y, and z, according to the Cartesian coordinates. The common applications are the following. Cylindrical. Cylindrical robots have a primary arm that moves up and down. Built within the robotic arm is a cylinder that creates this motion by extending and retracting itself. In many of these cylindrical robotic models, the rotation is generated by gears and a motor, and the vertical motion is generated using a pneumatic cylinder. The common applications are the following. Spherical. Polar robots are robot configurations with a combined linear joint and two rotary joints, with an arm connected to a robotic base and a twisting joint. The applications are the following. Articulated. The articulate configuration, also known as a revolute configuration, comprises a number of rigid arms connected by rotary joints. Rotary movement at the base is also provided. Since all movements are by angular rotation of the joints, complex calculations are often needed to move the arm in straight lines. Articulated configuration robot common application. SCARA. The term SCARA stands for Selective Compliance Assembly Robot Arm. It is a combination of cylindrical and revolute configuration operating in the horizontal plane. This type of configuration features two horizontal joints and a cylindrical work area. The common application of SCARA configuration robots. Gantry. A gantry robot consists of a manipulator mounted onto an overhead system that allows the movement across a horizontal plane. Gantry advantages. Gantry robot system provide the advantage of large work areas and better positioning accuracy. Gantry's common application. They are usually large systems that perform pick and place application, but they can also be used in welding and other applications. Actuators. An actuator is a part of a device or machine that helps it to achieve physical movement by converting energy, often electrical, air, or hydraulic, into mechanical force. It is the component in any machine that enables movement. Types of actuators. Linear actuator. An actuator can move something in a straight line. Rotary actuator. An actuator that can make something move in a circular motion. So what makes an actuator move? Actuators receive a source of energy and use it to move something. To put it in another way, the actuator converts a source of energy into physical mechanical motion. Hydraulic actuators use a variety of liquids as a source of energy. Electric actuators use some form of electric energy to operate. Pneumatic actuators are operated by compressed air. End effectors. An end effector is a peripheral device that attaches to a robot's wrist, allowing the robot to interact with its task. Most end effectors are mechanical or electromechanical and serve as a grippers, process tools, or sensors. Without an end effector, most robots are practically useless. An articulated robotic arm can be programmed to a particular location within its workspace, but without some sort of an end effector, it has no way to perform any operation. The three basic types of end effectors. The grippers. A gripper is a device which enables the holding of an object to be manipulated. A gripper enables holding, tightening, handling, and releasing of an object. A gripper is just one component of an automated system. A gripper can be attached to a robot or it can be part of a fixed automation system. Tools. Tools are used in applications where the robot must perform some processing operation on the work part. The robot therefore manipulates the tool relative to a stationary or slowly moving object. Examples of the tools used as end effectors by robots to perform processing applications include spot welding gun, arc welding tool, spray painting gun, rotating spindle for drilling, routing, grinding, and so forth, assembly tool, heating torch, and water jet cutting tool. Specifications. During the early stages of industrial robot buying process, a prospective buyer needs to decide on several factors regarding their industrial robot. Size, payload capacity, repeatability, reach, and other robotic specification play a major role in selecting the right robot arm for the industrial application. Common robot specification. Robot size in kilogram. The physical dimensions and weight of an industrial robot arm need to be considered to ensure that the robot arm will fit with the existing system and equipment already on the shop floor. Maximum payload capacity in kilogram. Industrial applications of robots and specifications often go hand in hand. Not only does the size and weight of the part need to be considered, but also the weight of the end of arm tooling should be added into the equation. Repeatability in millimeter. Repeatability refers to the ability of the robot arm to return to a previous point. Vertical and horizontal reach in millimeter. The reach capabilities of an industrial robot arm often play a major role in deciding whether the arm is right for the application. The robot arm needs to be able to reach all necessary areas of the part it is working on or system that it is working in.